we're going to talk about scale factor, and I think we've talked about it in some basic ways, and I want to make sure we solidify some of those ideas and extend them a little bit here. So a scale factor is a multiplier that can be used to enlarge or reduce a quantity. So if we have a proportional relationship or something that is similar, like these similar triangles down here, or like a recipe that we know we need to keep certain proportions true, we can use a scale factor to enlarge a recipe or to enlarge a shape or to reduce that recipe or to reduce that scale model. So scale factors are important because they help us to change things consistently. So for example, if you want to scale down a recipe that makes 6 servings so that it makes only 2 servings, you would need to multiply the quantity of each ingredient by 1/3 because we're thinking, all right, I normally make 6, but I want to make 2. So there's some number, there's some factor that I could multiply 6 by to get to 2. So to figure that out, this is kind of an easy example, but I could divide both sides by 6, and then I'd just be solving this simple equation to find what that scale factor is. X equals 2 over 6, 2 over 6, and that simplifies to 1/3. So we can always find the scale factor if we know the new amount that we want and we know the original amount. We can just set up a simple equation. You learned about scale factor when you dilated shapes, not in Chapter 2 or Chapter 4, but we've done this year. So for example, if the two similar shapes below are related by a scale factor of 5/4, that is kind of hard to read, but let's write that more clearly, 5/4, then the side lengths of the second triangle can be found by calculating an unknown times 5/4, this copy didn't work very well, 8 times 5/4 equals 10. And we probably might be given information like this is 8 and this is 10, and we need to figure out what that relationship is. We may not be given the scale factor, so we could think, well, 8 times some unknown equals 10. So how do I solve this equation? I divide both sides by 8, and I know that that something, this scale factor that I need to multiply by, is this 5/4, this simplified version of this. Sorry, that didn't come out very well. But what if I wanted to go the opposite direction? What if I knew that this was, what might this be? What if I knew that this was 11? How could I figure out what this unknown was? Well, if I wanted to go from 10 to 8, if 10 was my original, 10 times something equals 8. I can figure out the scale factor going the other direction. 10 is what I start with. I want to multiply it by something to get me to 8. And if I divide by 10, then I see that x, the opposite direction, is 4/5. I can simplify that. So if I wanted to find x, I could multiply the corresponding side 11 that I know the length of and find that 11 times 4/5 equals x, and that would be 44 divided by 5, so this equals 40 divided by 5 is 8, so 8 and 4/5. So if we have information, the new side compared to the old side, we can figure out what the scale factor is. And you'll notice something interesting. We've got a scale factor of 5/4 to get bigger and a scale factor of 4/5 to get smaller. And so down here, we can see a little bit more about this. The direction of scaling is important. In the above diagram, the scale factor from P to Q is 5/4. The scale factor from Q to P to go from that bigger to the smaller is 4/5. And if the scale factor in one direction is x, then we can just always say the scale factor in the other direction is the inverse of x, 1 over x. In other words, pairs of scale factors between similar shapes are reciprocals. 5/4 and 4/5 are the opposite of one another, the reciprocals of one another. The ratio of the perimeters of similar triangles is also equal to the scale factor. So if I added up the sides of all of those, the side of P, if I added up 8 plus 8 and 4/5 plus whatever this is, and added up these sides separately, and if I compared those two, we would always be able to compare them and see that the scale factor remains consistent, which is just kind of a little bonus piece of knowledge there. And the angles of similar triangles don't change at all. They are equal or congruent to one another. So if I change the side lengths, the angles stay the same. You'll see, you can kind of tell just from looking at it, the angle of Q didn't get bigger, or this angle within Q didn't get bigger. Side lengths can change, and the angles will stay the same if the triangles are truly similar. So in similar shapes, angles stay the same with enlargements and reductions, and the sides of similar triangles are proportional. They change in proportion to that scale factor, based on the scale factor, you could say. Okay, I'm going to pause this for now, and actually, yeah, I'm going to pause this and let you guys take a minute, and then we'll do the backside on a separate video.